Hi everyone, my name is Ayush Surawar and today I will present my project on the 1D CFD analysis of short shock tube. This presentation introduces the short shock tube problem, which is a fundamental setup in fluid dynamics for studying the behavior of the compressible fluids governed by the Euler equations. Short shock tube demonstrates the evolution of shock waves, rarefaction waves, and the contact discontinuities when a diaphragm separating two regions of a gas is suddenly removed. It serves as a critical benchmark for testing numerical schemes aimed at solving hyperbolic PDEs. This setup is significant because it mimics the real-world life scenarios like the pipeline ruptures and the shockwave propagation in aerospace. Let's now discuss the problem statement for this project. In the shock tube, on one side, the gas is initialized at the high pressure, 1 kilopascal high density, 1 kg per meter cube, while on the other side, it is at low pressure and low density. At time 0, the diaphragm is removed, introducing a discontinuity into the system. Here I implemented four numerical schemes: Lax-Friedrich, Lax-Wendorf, Rho, and Venno scheme. These equations are fundamental to modeling the conservation of the mass, momentum, and energy in compressible flows. To evaluate the performance of these schemes, I compared the numerical results with the analytical solution and carried out the spatial and the temporal convergence analysis. The analytical solution is being derived using the Raman problem. The algorithm is given here. The plot shows how the shock tube evolves. The pressure decreases sharply across the shock front, density drops in the rarefaction wave, velocity rises sharply at the contact discontinuity, and the specific internal energy highlights the region of the compression and the expansion. Now let's look at the Lax-Friedrich scheme. I begin by initializing the computational domain with the given initial conditions for pressure, density, and velocity on both sides of the diaphragm. The time step is also calculated using the CFL condition, which ensures stability. The Lax-Friedrich formula is applied to update the conserved variables. The method introduces numerical dissipation to stabilize the solution, and this process repeats on. Simulation parameters include 400 grid points, zero point 0.9 CFL, and end time of zero point 0.1 seconds. The plot shows the final state of the parameters such as pressure, velocity, density, and the specific internal energy. While the overall behavior aligns with the expectation, the scheme introduces some oscillations. Spatial convergence is carried out and it came out to be zero point 0.6, while the temporal convergence shows that the higher CFL number increases the L2 error. Let's now discuss the Lax-Wendorf scheme, which improves upon Lax-Friedrich scheme by incorporating a second-order accuracy. The scheme uses a two-step predictor-corrector approach. It accounts for both the flux and the Jacobian matrix to add second-order accuracy. Same simulation parameters were used. Oscillation near discontinuities are less pronounced but still present due to dispersion errors inherent into the scheme. The spatial convergence was carried out and the order came out to be 1.42, which is close to the second order, and the L2 error increases with the higher CFL number. Let's now explore the row scheme, which provides a more accurate solution by using locally linearized flux calculations. The row scheme uses row average values to approximate the solution at cell interfaces. The flux is computed with second order correction term, reducing dissipation while maintaining stability. Unlike the previous schemes, this row method directly accounts for the wave propagation physics, making it more precise near the discontinuities. The oscillation scenes in the Lax-Friedrich and the Lax-Wendorf are almost completely eliminated, indicating minimal numerical dispersion. The row scheme achieves a convergence order of 0.9132, and its temporal convergence shows that the L2 error increases with higher CFL numbers, but the runtime decreases significantly. Finally, let's examine the Vino method. Here, the flux at the cell interfaces is reconstructed using a combination of fluxes from the neighboring points, and the weights are adaptively calculated to minimize oscillations, especially near discontinuities. Thereafter, the conserved variables U are updated using the reconstructed fluxes and the time steps calculated with the CFL condition. The plot shows that the sharp resolution of the shock and refraction waves without any oscillations. It is clean and accurate profile with minimal numerical artifacts. Compared to earlier scheme, Vino achieves the best balance of accuracy and the stability. It has a convergence order of 1.03 at discontinuities. As with the other methods, higher CFL number leads to increased L2 error but reduced runtime, indicating good computational efficiency. Here it is compared the performance of all the numerical schemes. Lax-Friedrich deviates significantly from the analytical solution, while Lax-Wendorf comes closer to the analytical solution. Row scheme seems to pretty much matches with the results, while the Vino scheme achieves the closest match to the analytical solution. Here I have compared all the four schemes with different parameters, and to conclude, for baseline studies, lax matrix or lax Voltovs are appropriate, offering simplicity at the cost of accuracy. For real-world application, Rho and Vino schemes stand out, with Vino being the top choice for the problems where accuracy outweighs computational cost. The choice of the scheme depends on the trade-off between computational resources and the required accuracy for the problem at hand. In conclusion, each scheme has its strengths and limitations. By understanding this, we can choose the most suitable method for the specific requirement of a problem. Thank you.